Okay, hello students, welcome back. So let me share the next presentation, which is about solar modules. Okay, let me first students, welcome back.
A definition
of a solar
module. I mean, in the first presentation, we had already
about
some intuitive explanation. Now I want to be a little bit more precise. So a photovoltaic module or photovoltaic solar module is a module of solar cells.
Okay, let me first
Students are electrically connected and mechanically assembled and encapsulated solar cells, such to get an electrotechnical device which represents the smallest installation unit for converting light into electricity in photovoltaic systems. And this interconnection to modules is necessary for several reasons. One is a single solar cell just supplies a voltage of roughly half the band gap. That means in crystalline silicon, it's half a volt typically. And but for the operation of electrical devices, usually higher voltages are needed. And the next is, the transmission losses. In the so-called ohmic losses, they are the less, the higher the voltage and the lower the current. Therefore, it's usually of advantage to have large voltages and small currents. Then, of course, one must get practical and manageable units, installation units. And then, of course, the solar cells must be protected against environmental impact. And all these serves the solar module. I want to warn laymen sometimes confuse solar modules, which are photovoltaic devices, and solar thermal collectors. These are, of course, two completely different devices and should not be confused. This picture you saw already several times in different versions. Now I have here this red dashed frame around what is here called on the crystalline silicon technology line module fabrication, and here on the thin film line we know already basically the module is already made together with the solar cell, at least essential parts of the module, not the whole module, but more than half of the module is already made together with the solar cell. Whereas in crystalline silicon technology, we get here the cells, and then we have to assemble from the cells the module. And typically, here in crystalline silicon technology, a module manufacturer does not manufacture at the same time the cells. That means typically a module manufacturer purchases the cells from another company which makes the cells and then makes the modules out of it. The reason is because these are completely different technologies. As we saw in one of the previous course lessons, this is basically semiconductor technology, where this one is either classical mechanical engineering or classical electrical manufacturing. Here I have the typical structure of a crystalline silicon solar module, and let me remind you, crystalline silicon is 95% of the market. So that means it's by far the most important one. And what is here first shown, this is a standard module with lamination plastics film of a substance which is usually called EVA, which is the most used substance or the most used polymer. It's ethylene vinyl acetate. And what we see here, the solar cells themselves, they are embedded in this EVA, which happens by a lamination process, as we will see later. Originally, these are two sheets of this EVA, and between these two sheets, we have here the cells, and then under vacuum, these two sheets are heated, and then they glue together here. I mean, like, one cannot recognize any longer the original interface, and they adhere also very much to the solar cells, and that means the solar cells themselves are well embedded in this EVA. And I should say there are also other materials which can be used, but EVA is still the dominating one. And then the standard module on the front side, it has a glass pane. It's a special glass. This glass is highly transparent. That means it has a higher transparency than, for example, ordinary window glass, which is reached by using special sands by which this glass is made, which have a very low iron content. Ordinary window glass has an iron content below 500 ppm. Solar glass has an iron content below 150 ppm. That makes it more transparent, and you can also recognize, for example, if you look at the edges of normal window glass, you see these edges are greenish, whereas for solar glass they're really white, and this is why this solar glass is also called white glass. Okay, on the back side, in a standard module, we have a foil. Okay, this could be a so-called Tetlar foil, or Tetlar. It's just a trade name, but there are various materials. Usually this is a multiple layer laminate also, because there is no single foil material which serves all the properties, or which has all the properties which are needed. Okay, and this stack of glass EVA with embedded cells and backside foils, you see it's usually in a aluminum frame, and here of course we need some sealing to keep it tight here in this frame. And the cells within each other are always connected with these connection ribbons. This is usually tinned copper ribbons, and you see they always go from the front side of one cell to the back side of the other cell. And they're just soldered to the bus bars on the front side and to the solder pads at the back side. And it's clear that this is an electrotechnical series connection, what we see here. Okay, in a whole module, the standard configuration is that all the cells are in series. And this is here indicated by these red lines. Okay, this is, for example, a 60-cell modules, which is one of the standard modules. Every cell neighboring to every two neighboring cells are connected in this way, as shown before, front side of one cell to back side of the other cell. And this in this sequence, okay, here we have some transverse solder ribbons, and that means in a standard module, as here indicated by the red line, all the 60 cells are in series. There are exemptions, but this is a small percentage in the market. For example, there's an exemption for so-called half-cell modules. They're usually half of a module is only in series, and then the two series strings are connected to each other in parallel. And the reason is that for the total module, one wants to get the same properties as for this module here, where for the standard module, where all 60 cells are connected electrotechnically in series. And here you see this would be the two terminals of the cell, and they are led to the backside of this cell. They are led to the backside where the so-called junction box is connected to the cell, where the connection then the electrotechnical connection is then made in the installation of this solar module. Okay, here's again a schematic view how this happens. Okay, schematically, we always have a front side with the back side connected. Okay, from the top view, it's not so easily seen, but from the side view, it becomes clear. And that means for the standard cell, at the end, where we have the top connected, it's a minus pole, and where we have the bottom connected, it's the plus pole. And it's also clear if we have the series connection of n cells, then the total voltage is just the sum of the voltages of the single cells. That it means it's roughly n times the voltage of the single cell, or it would be precisely n times the voltage of the single cell if all the voltages would be precisely the same. But in reality, of course, we always have some scatter, because in reality, of course, we cannot manufacture two cells which are 100% identical to each other. For the current, for the total current, of course, we have the total current is equal to the current through a single of the cells, again, if all the cells have the same current. And for this current, I mean, you see, if we would have a cell with a lower voltage, it would be uncritical, because then, of course, the total voltage would be less, but it would not affect the voltages which is contributed by the other cells. But if we would have one weak cell with a lower current, then, of course, also the total current would be almost the same as this current of the weakest cell, and therefore sorting of the cells with respect to current is necessary. And then usually only cells which are very similar to each other with respect to the current are used in one module, and then usually one has several bin classes of currents, and then several bin classes of modules are produced. That means if you look in the data sheets of manufacturer, you usually see modules which slightly vary just by the amount of their short circuit current. Okay, here I will give you some typical values for cells. I mean, the first one is the short circuit current density, because the current density, of course, is a physical parameter. It's clear that the current scales with the cell. 15 times 6 times 15 times 6 was for a decade the dominating size, and is still in this range is still the dominating cell size. And you see the current density is typically between 30 and 40 milliamps per square centimeter, which means a current of 7.3 to 10 amps for the standard cell size. Okay, the open circuit voltage is between 0.6 and 0.7 volts. That means that the maximum power point voltage is slightly less. It's around half a volt, as I mentioned already. And that means then typical values for modules. I mean, typical module sizes have been 36 volt cells, but there's still some of these modules in the market. Then the standard sizes, meanwhile, are 60 cells or 72 cells. And then for 36 cells, we have an MPP between 16 and 20 volts. For 60 cells, between 27 and 38. And for 72 cells, between 32 and 40 volts. The 36 and the 72 are just well fitted for charging batteries of 12 volts and 24 volts. And therefore, of course, in the initial days where not so many applications were for grid connection, these were the dominating cell sizes. Meanwhile, the standard is, or was for a decade, is what 60 cells. Meanwhile, we see again increasingly 72 cells in one module. But in principle, of course, you can make any size where you have just a certain column times column times row. That means if this fits, of course, you could make a module. And I mean, these are just the most prominent sizes, but they're, of course, for special applications, you might also find other sizes. Okay, let me remind you of the IV curve of such a module. Okay, you see that would be the blue curve would be the IV curve, where here we have the open circuit voltage. Here we have the short circuit point, and if we just calculate the power is just current times voltage. We get the red curve, and at some point we have a maximum, and therefore this is called the MPP, the maximum power point. Okay, here we also see the maximum power point in the IV curve of the cell. Okay, that would be an example for a small module of only 50 watts. A standard module has between 250 and 300 watts. Okay, this is an overview how such a module is manufactured. Okay, the first thing what you have to do, or it could also have been already done at your cell supplier, is to test the cells. Here you see the IV curve is recorded, and you make the sorting. This is what I mentioned, because the short circuit currents of the different cells must fit together, because else the weakest cell would determine the current of the whole string. Okay, then the string layout is done, and the cells are soldered to each other in this way, as I mentioned already, always from the front side to the back side, front side to back side, such that we get a series connection of all these cells. Okay, then one has a visual inspection, and then the string layout for matrix configuration is done. That means you see, that means the parallel strings are put to each other, and here at the edges there's a transverse soldering done, such that again we have a series connection of all these strings. And you see here we have the layout of this